Tonight, we're going to look at what the James Webb Space Telescope found when it turned its eyes to the most distant light in the observable universe. Webb was built to answer one of cosmology's oldest questions. What did the very first galaxies look like, and when did they form? Its designers knew what to expect. 6 decades of theoretical work, of simulations, of careful modeling. The standard picture of how the universe evolved was detailed and specific. Specific enough that astronomers preparing to analyze Webb's data had written papers in advance predicting what the telescope would find. Not guesses, not vague expectations. Quantitative predictions with error bars grounded in the most sophisticated computational models of cosmic evolution ever built. Webb was supposed to confirm them. What it found instead is not something the standard picture predicted, not even close. In the earliest, deepest images Webb has ever captured, astronomers found galaxies that were too massive, too structured, and too chemically complex to exist so early in cosmic history. They found evidence of stars that had already lived and died in a universe less than 3% of its current age. They found a galaxy formed just 290 million years after the Big Bang, already showing the chemical fingerprints of multiple stellar generations, fingerprints that can only be written by the deaths of earlier stars. And separately, in a line of investigation that began before Webb even launched, they found that 2 independent measurements of the universe's expansion rate refused to agree with each other. Not by a small margin, not by an amount that might be explained by a single miscalibrated instrument or a single overlooked correction factor, by an amount that every recalibration, every additional decade of data, every improved instrument has failed to close. Both problems are real. Both are confirmed. Neither is yet explained. By the end of tonight, you're going to understand what Webb found, why it matters, what the most distinguished physicists alive are doing about it, and why one of them, a Nobel Prize winner who has spent 20 years developing an idea the mainstream has been slow to accept, has now found his work mentioned in the same breath as James Webb's most anomalous discoveries. If you'd like to spend more nights exploring the edges of what we know, consider subscribing to Slow Orbits. It helps keep this channel going, and it means there will be more journeys like this one. Now, let's begin. The James Webb Space Telescope did not arrive quickly. The first serious proposals date to 1989. The Hubble Space Telescope had not yet launched. The World Wide Web would not exist for another 2 years. The Berlin Wall was still standing. And a group of astronomers, gathered for a workshop on the future of space astronomy, began describing an instrument so ambitious that the most optimistic among them thought it might take 15 years to build. It took 32. The journey from that 1989 workshop to Christmas Day 2021 passed through budget battles that nearly killed the project, a launch delay that stretched years past its original schedule, and a cost overrun so dramatic that Congress came close to canceling the telescope entirely. In 2005, a senior NASA administrator testified that Webb had become one of the most technically challenging projects NASA had ever undertaken. In 2011, a House Appropriations Subcommittee voted to cancel it outright. The scientific community mobilized, Letters went to Congress. The vote was overturned. The project continued. By the time Webb launched, it had cost approximately $10 billion. That number is worth sitting with. $10 billion for a single scientific instrument for a telescope. It is more than many countries spend on their entire space programs in a decade. And yet, once you understand what Webb was trying to do, the investment begins to make sense. Hubble had been revelatory. Since its own launch in 1990, it had given humanity its first truly clear view from above the blur of Earth's atmosphere. Crisp images of nebulae, of dying stars, of galaxies colliding in slow gravitational embrace. It had measured the expansion rate of the universe. It had observed the most distant galaxies anyone had ever seen. And it had done all of this while orbiting just a few hundred kilometers above the surface, close enough that astronauts could fly up in the space shuttle and repair it, which, famously, they had to do within the first few years of operation, when engineers discovered that Hubble's primary mirror had been polished to precisely the wrong shape. The mirror was perfect. It was perfectly wrong. The flaw was smaller than a fraction of the width of a human hair, and it ruined every image. After a shuttle repair mission fitted corrective optics, a fix as audacious as anything in the history of astronomy, Hubble became the instrument it was supposed to be. But Webb was designed to do something Hubble couldn't. Hubble works primarily in visible light, the same narrow range of wavelengths that human eyes detect. Webb was designed to work in the infrared, and the difference between those two choices is not merely technical. It is the difference between being able to see the universe's first galaxies and not being able to see them at all. Here is why. When the first galaxies formed, they emitted light across ultraviolet and visible wavelengths, the light of young, hot stars blazing into a cosmos that had never seen starlight before. But the universe has been expanding since those photons departed, and when space itself expands, the wavelength of light traveling through it stretches along with space. The further the source, the longer those photons have been traveling, and the more they have stretched. Light that left a galaxy 13.5 billion years ago, light emitted as ultraviolet radiation, arrives at Earth today shifted far into the infrared. It is invisible to Hubble, invisible to the naked eye, detectable only by an instrument specifically designed to catch those long wavelength infrared photons. Webb was that instrument, and it was not merely a larger Hubble. The design choices that set Webb apart were systematic, each one following from the requirement to detect infrared light from the most distant sources in the observable universe. Its primary mirror is 6.5 meters across, 21 feet from edge to edge. That sounds like a modest increase over Hubble's 2.4-meter mirror, until you remember that light gathering power scales with the area of the mirror, not its diameter, and area scales with the square of the radius. Webb's primary mirror has a light collecting area of approximately 25.4 square meters compared to Hubble's 4.5 square meters, nearly 6 times the light gathering power. Webb can detect sources that Hubble would miss entirely. But a 6.5-meter mirror presents an engineering problem with no easy solution. No rocket fairing in existence, not then, not now, is wide enough to carry a single rigid mirror of that size. It simply won't fit. So engineers designed it in sections, 18 hexagonal segments, each cast from beryllium, a metal chosen for its extraordinary stiffness to mass ratio and its dimensional stability across extreme temperature changes. Steel expands and contracts significantly as temperature shifts. Aluminum does. Even glass does. Beryllium, by comparison, is almost dimensionally inert across an enormous range of conditions. This matters when you are trying to maintain nanometer-level alignment between mirror segments in the brutal thermal environment of space, where sunlit surfaces can reach temperatures far above boiling water, and shadowed surfaces drop to hundreds of degrees below. Each segment was ground to an exquisitely precise curved shape, and then coated in a microscopically thin layer of gold. Not gold for decoration, gold because it reflects infrared light better than silver or aluminum, the more common choices for telescope mirrors. Gold's reflectivity in the near-infrared wavelengths Webb observes is approximately 98%. That tiny difference matters when you are trying to detect light from a galaxy that has been traveling for 13.5 billion years. The gold layer is so thin that if you scraped all of it off all 18 segments, you would have roughly 48 grams of gold, about the weight of a golf ball. These segments fold inward for launch, like petals pressing closed, and then unfold in sequence once in space. That unfolding was one of many steps in what NASA called the most complex spacecraft deployment ever attempted. Because the mirror was only one of Webb's challenges, infrared detectors are extraordinarily sensitive to heat. Any warmth from the sun, from Earth, from the moon, from the telescope's own structure, produces infrared radiation that would overwhelm the faint, ancient light Webb was trying to detect. The telescope needed to be cold. Its near-infrared camera, near-infrared spectrograph, and other instruments needed to operate at approximately negative 233 degrees Celsius, just 40 degrees above absolute zero. Its mid-infrared instrument needed to be even colder, below negative 266 degrees Celsius, achieved through a mechanical cryocooler that Webb carries as part of its instrument suite. Colder than the surface of Pluto, colder than almost anything in the solar system, colder than anything humanity had ever launched into space that needed to keep functioning reliably for a decade or more. To achieve this cooling passively for the main instruments, engineers at Northrop Grumman designed a sun shield. It is 22 meters long and 12 meters wide, roughly the size of a tennis court. It consists of 5 layers of a plastic-like material called capton, each layer thinner than a human hair, each coated on both sides to reflect incoming radiation and emit outgoing heat. The layers are not touching, there are gaps between them, and in those gaps, heat radiates from the warmer, lower layer into the space between, where it is radiated away into the vacuum before it reaches the next layer above. 5 layers, each stepping the temperature down further than the last. Together, these 5 layers reduce the temperature from the sun-facing side to the instrument-facing side by nearly 300 degrees Celsius. On a normal operating day, the hot side of the sun shield reaches approximately 85 degrees Celsius. The cold side, behind all 5 layers, sits at approximately negative 233. That temperature difference, achieved over about 5 meters of stacked Kapton film, is one of the quiet engineering achievements of the 21st century. No moving parts, no active cooling on that side, just physics, exploited with extraordinary precision. Webb launched on Christmas Day 2021 at 12:20 in the morning, Coordinated Universal Time, from the European Space Agency's launch facility in Kourou, French Guiana. It rode an Ariane 5 rocket, a vehicle with an exceptional reliability record across more than 100 launches, on a trajectory not to low Earth orbit, where Hubble circles, but to a gravitational equilibrium point nearly 1 million miles from Earth. This point is called the second Lagrange point, or L2. L2 is a location where the combined gravitational influence of the Earth and the Sun balances against the tendency of an orbiting body to drift. At L2, the Earth and the Sun are always in the same direction relative to the spacecraft, both behind the telescope in the direction the sun shield faces. Webb can keep its sun shield between itself and both heat sources simultaneously at all times. There is no such arrangement in low Earth orbit. Hubble passes in and out of Earth's shadow dozens of times per day. Webb never does. The journey to L2 took approximately 30 days. The deployment sequence began almost immediately after separation from the rocket. Over the first 2 weeks, the sun shield pallets folded out. The 5 Kapton membranes unfurled, one by one, tensioning into place. The secondary mirror, positioned on 3 folding struts extending forward of the primary mirror, swung forward and locked. Then, over several days, the primary mirror segments unfolded from their launch locks, one side of the mirror structure, then the other, the 18 hexagonal petals opening in a careful sequence. None of it could be fully tested before launch. The delicate sun shield membranes cannot be deployed in the gravity and atmosphere of Earth without special equipment that is impossible to scale to the full size of the flight unit. The mechanical behavior of the mirrors under vacuum conditions and in the absence of gravity cannot be fully replicated in a test chamber. Engineers could test components. They could simulate. They could run deployments of individual elements, but the actual deployment, all 344 individual mechanisms involved in it, all classified as single-point failures, meaning a single mechanism failing could cost the entire mission, could only be verified once, in space, 1,000,000 miles from anyone who could intervene. Everything worked. The alignment of the mirror segments alone then took 3 months. Engineers sent commands to the actuators behind each mirror segment, small precision motors capable of moving the segments by as little as 1 nanometer, thousands of times over 12 weeks, using observations of carefully chosen bright stars to triangulate the exact position and orientation of every mirror piece. The goal was to make 18 separate mirrors behave as a single optical surface with alignment errors no larger than 150 nanometers, 150 billionths of a meter, across a mirror 6.5 meters wide. To calibrate, engineers used a bright infrared star designated to a mass J17554042655127, unremarkable in every way except brightness and stability. They imaged it, analyzed the deviations in the stellar point spread function, calculated exactly how each segment needed to move, moved it, then measured again. thousands of individual actuator commands over 12 weeks. They achieved a final wavefront error of less than 8 nanometers. To put that in physical terms, the height variation across the entire primary mirror, averaged across its full 6.5-meter expanse, is less than 1/20th the wavelength of visible light. It is the most precisely shaped large optical surface ever built. Webb carries 4 main science instruments. The near-infrared camera, called NIRCam, is the primary imaging instrument. It captures the detailed pictures of galaxies and nebulae that most people associate with Webb's images in wavelengths between 0.6 and 5 microns. The near-infrared spectrograph, NIR-SPEC, is perhaps the most scientifically powerful instrument. It can simultaneously measure the full spectra of up to 100 objects in a single observation using a micro-shutter assembly. A grid of 250,000 individually commandable doors, each smaller than the width of a human hair, that can open over specific targets in the field of view while remaining closed over everything else. This is how James was able to characterize hundreds of distant galaxies in the time it would have taken Hubble to characterize one. The mid-infrared instrument, MIRI, extends Webb's capabilities to longer wavelengths, from 5 to 28 microns, where dust emission from star-forming regions becomes bright and where the coolest, most distant galaxies emit most of their light. MIRI requires the coldest temperatures of any Webb instrument, below -266 degrees Celsius, achieved with its dedicated mechanical cryo-cooler. And the fine guidance sensor, combined with the near-infrared imager and slitless spectrograph, provides the precision pointing control that allows Webb to hold its gaze on a target for hours at a time. Accumulated photons without drift. These 4 instruments together give Webb capabilities across wavelengths and scientific techniques that no previous space observatory had combined. On July 12, 2022, NASA released Webb's first science images. The reaction was extraordinary. Deep field images showing thousands of galaxies in a patch of sky smaller than a grain of sand held at arm's length. Galaxy clusters bending the light of objects behind them into arcs and curves. Einstein's general relativity made visible in the distant sky. Stellar nurseries resolved into 3-dimensional structures of gas and dust, carved by the radiation pressure of newborn stars into shapes that had never been seen at this resolution. Exoplanet atmospheres analyzed in a single observation for water vapor, carbon dioxide, and methane. The first deep field image used a cluster of galaxies called SMACS 0723 as a gravitational lens. In the area of sky a grain of sand would cover, Webb revealed thousands of individual galaxies, ellipticals glowing red with old stellar populations, distant spirals mid-rotation, and lensed arcs of blue and white from objects so far behind the cluster that their light had been bent and magnified by the intervening gravity into curves across the field. Webb's near-infrared spectrograph simultaneously measured the redshifts and chemical compositions of dozens of these lensed background galaxies, analysis that would have taken Hubble weeks per target. The images were remarkable. They were also, as it quickly became clear, not the most important thing Webb was about to show the world. Because behind the spectacle, behind the headlines and the press releases, In the data flowing down from Webb to research teams around the world, something was present that no official announcement mentioned, something unexpected. To understand what Webb found, you need to understand what it was supposed to find. And to understand that, you need to understand the model. Cosmologists call it lambda CDM. The Greek letter lambda represents the cosmological constant, a property of empty space itself that causes the universe's expansion to accelerate, what we commonly call dark energy. CDM stands for cold, dark matter, a hypothetical form of matter that doesn't interact with light in any detectable way, can't be seen or touched or directly measured, but exerts gravitational influence on ordinary matter, pulling it together, shaping how galaxies and clusters of galaxies form and evolve. Together, dark energy and dark matter account for approximately 95% of the total energy content of the universe by the model's accounting. Ordinary matter, everything made of protons, neutrons, and electrons, everything you have ever seen or touched or breathed, makes up the remaining 5%. This model has been extraordinarily successful. It correctly predicts the distribution of galaxies on the largest scales, the great filaments and voids, the clusters and superclusters, the foam-like cosmic web of structure that spans the observable universe. It matches the detailed fluctuations in the cosmic microwave background with precision that is, in the measurement business, almost embarrassingly good. It correctly predicts the proportions of hydrogen and helium produced in the first few minutes after the Big Bang, matched to observations accurate to within a fraction of a percent. Lambda CDM is one of the most rigorously tested theoretical frameworks in the history of science, and it makes very specific predictions about the early universe. The universe began approximately 13.8 billion years ago, not an approximation. This age is derived from multiple independent measurements, and the approaches agree to within a small fraction of a percent. In the first fractions of a second, the universe was unimaginably hot and dense, 1 billion times hotter than the core of the sun. Matter and energy in a state that no laboratory on Earth has ever reproduced. Within the first 3 minutes, the temperature had dropped enough for nuclear fusion to briefly ignite. Protons and neutrons fused into the nuclei of hydrogen, helium, and trace amounts of lithium, the first elements. Roughly 75% hydrogen, 25% helium, and fractions of a percent of everything else, confirmed by observation to extraordinary precision. For the next 380,000 years, the universe remained a hot, dense, opaque plasma. Photons could not travel freely. They were constantly scattering off a sea of free electrons. Think of the interior of the sun, which is opaque for the same reason. Light generated by fusion in the solar core takes tens of thousands of years to work its way outward because it scatters constantly. The early universe was like this, but everywhere. Then, as the universe cooled past about 3,000 degrees Kelvin, protons and electrons finally had enough energy taken from them by the expanding universe to combine. Neutral hydrogen atoms formed across the entire cosmos, almost simultaneously. The fog cleared. Photons that had been trapped, scattering endlessly, suddenly had a clear path through the universe for the first time. They streamed outward in every direction. That light from the moment the universe became transparent, is still traveling today. We detect it as the cosmic microwave background, cooled by 13.8 billion years of expansion from its original 3,000 degrees down to 2.7 degrees above absolute zero, stretched from visible light down into the microwave band, but still present, still detectable, and still carrying in its subtle temperature fluctuations, 1 part in 100,000, the imprints of the structures that would eventually grow into every galaxy and cluster in the observable universe. After the CMB was released, the universe went dark. There were no stars, no galaxies, no light of any kind, except the fading glow of the CMB itself, cooling as the universe expanded. Just vast, largely uniform clouds of hydrogen and helium gas, slowly drifting, slowly being pulled by gravity into the slight overdensities that quantum fluctuations had seeded into the universe in its very first moments. Cosmologists call this period the cosmic dark ages, from roughly 380,000 years to perhaps 150 to 200 million years after the Big Bang, a stretch of time longer than the entire era of the dinosaurs. The universe contained nothing that emitted visible light. If you could have placed yourself anywhere in space during the Dark Ages, you would have seen complete blackness. Then gravity won the slow tug of war. In the regions where the gas was slightly denser than average, that density advantage acted as a gravitational seed. It attracted more gas. The cloud collapsed slowly at first, then faster as increasing density strengthened the gravitational pull. The core grew hot enough to ignite nuclear fusion. The first stars lit up. These population 3 stars, the name comes from the astronomical convention of naming stellar generations in reverse order, with today's metal-rich stars as population 1, older depleted stars as population 2, and the primordial first generation as population 3, formed from gas that was almost entirely hydrogen and helium. The absence of heavy elements changes the behavior of a collapsing gas cloud fundamentally. Without the cooling mechanisms that heavier elements provide, the gas must collapse to much higher densities before star formation triggers. This produces more massive stars. Models suggest population 3 stars may have been 100 to several hundred times the mass of our Sun. Possibly more. No population 3 star has ever been directly observed. They are believed to have lived and died before the first galaxies were fully assembled, in an era too early and too distant for any instrument built so far to image directly. But stellar physics allows us to predict what they were like and how they died. Stars of that mass burn through their fuel in millions of years rather than billions. They die in supernovae of extraordinary energy, some so energetic that the star is entirely disrupted, leaving no remnant, or collapse directly into black holes of tens or hundreds of solar masses. And in dying, they scatter into the surrounding gas everything their fusion reactions had built: carbon, oxygen, silicon, magnesium, iron, every element heavier than lithium that exists in your body, in your bones, in your blood, in the cells doing the work of keeping you alive right now, was forged in the interior of a star and scattered by its death. The gas enriched. Later, stellar generations formed from that enriched gas. They were cooler, longer-lived, more like our Sun. They gathered into proto-galaxies, small, irregular systems of millions of stars held together by gravity. Over billions of years, those proto-galaxies merged. Larger structures consumed smaller neighbors. The Milky Way, with its hundreds of billions of stars and its thick disk, and its central bar, and its halo of globular clusters, is the product of billions of years of this gradual gravitational accumulation. This is Lambda CDM's story of cosmic structure formation, hierarchical and slow. Small things first, larger things built from smaller parts over very long time scales. The specific, quantitative predictions that follow from this story are detailed and precise. Computational programs like Illustris TNG, one of the most sophisticated cosmological simulations ever run, involving billions of resolution elements tracking dark matter, gas, stars, and black holes through 13.8 billion years of simulated cosmic evolution, produced specific numbers for the high redshift galaxy population. For how many galaxies should exist at each epoch, how massive they should be, how fast they should be forming stars. Illustris TNG predicted that galaxies with stellar masses above 10 billion solar masses, systems containing at least 10 billion times the mass of our Sun, should be extremely rare at redshift 10, corresponding to about 480 million years after the Big Bang. Different simulation teams using different codes, different computational methods, different assumptions about feedback physics converged on broadly similar numbers. The EAGLE simulation, developed by a consortium of European universities, reached similar conclusions using a different computational approach. The FIRE simulations, developed at Caltech and other institutions, produced high-resolution models of individual galaxy formation that showed how feedback from stars and black holes regulated star formation in early systems, keeping stellar masses well below the levels that would be physically implausible. These simulations were not idle guesses. They were tested against the galaxy populations that Hubble had observed, galaxy number counts, size distributions, color magnitude relations, at redshifts where Hubble could reach. They reproduced the observed galaxy populations reasonably well in these tested regimes. The extrapolation to higher redshifts, to the epoch Webb would probe, was therefore grounded in models that had been calibrated against available data. And yet those models were calibrated against data from a regime where the universe was already billions of years old. The first few 100 million years, the epoch that was always Webb's primary scientific target, remained unconstrained by direct observation. The simulations were extrapolating into the unknown, guided only by the physics they had been built from. The prediction for what Webb would find at the very earliest epochs was specific: small, irregular, faint proto-galaxies, mostly hydrogen and helium, with few stars, no significant chemical complexity, and stellar masses far below what mature galaxies would eventually achieve. The seeds of structure, not structure itself. This is what astronomers expected. It is not what they found. The first hints appeared almost immediately. In the deep field, images released in Webb's first months of operation, the teams working with the early data noticed several objects that appeared redder than expected. Not subtly redder, dramatically redder. Red in the specific way that cosmological redshift makes very distant galaxies appear. Their light stretched toward the infrared by billions of years of traveling through expanding space. Initial analyses flagged them as high redshift candidates, possibly very high redshift candidates. Initial caution was appropriate. The method used for these early identifications was photometric redshift estimation, comparing an object's brightness across multiple filtered wavelength bands to find the color pattern that indicates how much its light has been stretched by the universe's expansion. Photometric redshifts are useful for scanning large numbers of objects quickly, but they can be wrong. They can be fooled by unusual dust reddening, which makes a nearby galaxy appear red for completely different reasons than a truly distant one. They can misidentify the spectral signature of one type of object as the redshift pattern of another. The candidates needed spectroscopic confirmation, the definitive measurement that disperses a galaxy's light into its complete spectrum and allows precise identification of known atomic transition wavelengths from which an exact redshift can be calculated without ambiguity. The community waited, and what came back as spectroscopic data accumulated and teams worked through their analysis became a paper published in the journal Nature in early 2023. Astronomer Ivo Labbé of Swinburne University of Technology and his colleagues had identified 6 candidate galaxies in Webb's early imaging. All appeared from their spectral energy distributions to be observed when the universe was between roughly 500 and 700 million years old. That epoch, the first 5% of cosmic history, is precisely where Lambda CDM's predictions for galaxy populations were most specific and most testable. But it was not their era that prompted the paper. It was their apparent mass. For each candidate, the team estimated the total stellar mass, the aggregate mass of stars the galaxy appeared to contain. The estimation method fits the observed pattern of brightness at different wavelengths to models of stellar populations, finding the combination of stellar ages and compositions that best reproduces the observed spectral energy distribution. The mass estimates that came back were astonishing. In the standard model, at an epoch between 500 and 700 million years after the Big Bang, the most massive galaxies should contain perhaps a few billion solar masses, a few percent of the Milky Way's stellar mass, structures in the early stages of assembly. These candidates appeared to contain 10 billion solar masses, or 50 billion. One candidate appeared to contain roughly the stellar mass of the entire Milky Way, a galaxy that had assembled between 100 and 400 billion solar masses of stars in less than 700 million years. Here is what makes that remarkable. The Milky Way contains between 100 and 400 billion stars. It has been building that stellar population for approximately 13 billion years. It has had enormous time to gather gas from the surrounding intergalactic medium, to pull in smaller satellite galaxies through gravitational accretion, to form stars from that gas, to have those stars enrich the remaining gas with heavy elements through their deaths, and to repeat this cycle over and over. 13 billion years of accumulation. These candidates appeared to have comparable stellar mass when the universe was 5% of its current age. For this to be physically possible within the standard framework, the star formation efficiency would need to be extraordinary. Efficiency in this context means the fraction of available gas that actually collapses into stars rather than being expelled or prevented from collapsing by the feedback processes that regulate star formation. In the universe today, star formation efficiency is typically a few percent. In the most extreme starburst galaxies known, it rarely exceeds 30 to 40%. Labbé's team calculated the required efficiency for each candidate. For the galaxies at redshift around 7.4, roughly 700 million years after the Big Bang, the required efficiency was approximately 57%. Surprising, but not strictly impossible if early feedback was very different from today. For the most extreme candidate, at redshift around 9.1, roughly 550 million years, the efficiency required approached 100%. 100% star formation efficiency. Every atom of hydrogen in the available gas pool collapsing into a star. Nothing expelled, nothing prevented, nothing left over. That is not what physics allows. Michael Boylan Colkin at the University of Texas at Austin examined the situation more carefully in a 2023 paper in Nature Astronomy. He ran a statistical analysis asking not whether any individual candidate galaxy was physically possible, but whether the population of massive early galaxies that Webb was finding was statistically consistent with lambda CDM, given the specific volumes of the universe that Webb's observations were sampling. His conclusion was that the most extreme candidates created tension with the model that was not easily dismissed. He used careful, calibrated language, the language of someone who understands that a tension is not a refutation. But the implication was clear. The standard framework was struggling to account for what Webb was seeing. The astronomy community's first response was calibrated skepticism, and that skepticism turned out to be partially justified. Active galactic nuclei, AGN, are the bright, energetic regions surrounding supermassive black holes at the centers of galaxies, regions where matter falling onto the black hole releases enormous amounts of radiation. An AGN can outshine all the stars in its host galaxy combined. If some of Labbé's candidates had luminous AGN at their cores, their apparent brightness would be far greater than their stellar populations alone would produce. Their stellar mass estimates, which are derived from that brightness, would be wildly overestimated. Subsequent spectroscopic follow-up of the most extreme candidates confirmed AGN contamination in some cases. The most extreme mass estimates turned out to be quasars, not massive stellar systems at all, but extremely bright black holes masquerading as massive galaxies in the photometric analysis. But not all of them. A subset of the original candidates survived careful scrutiny, not the most extreme ones, but enough galaxies at redshifts and masses inconsistent with model predictions to constitute a genuine statistical anomaly. Different research teams, working independently in different sky fields with different Webb instrument modes, arrived at the same conclusion. The excess of massive early galaxies is real. The standard model underpredicts the population. not by the dramatic factor the earliest photometric estimates suggested, but by a factor that is consistently there, consistently pointing in the same direction, and consistently resistant to being explained away by any single systematic effect. The reaction of the galaxy formation community to these findings is worth describing because it illustrates how science actually processes surprising results. The immediate instinct, rightfully, was skepticism. Photometric redshifts are uncertain, mass estimates from photometry can be wrong, AGN contamination is real. Every experienced astronomer in the field knew these things, and every careful analysis of the Webb data applied these corrections. What remained after the corrections is what matters, and what remained was a population of galaxies more massive than predicted, at redshifts higher than where models suggested such masses should be possible. Several independent analyses followed. One approach looked at the specific star formation rate, not the total stellar mass, but how fast the stars were being produced per unit of existing stellar mass. Galaxies at the most extreme redshifts showed specific star formation rates far higher than local analogues, consistent with rapid early assembly but difficult to reconcile with the available cosmic time under standard formation models. Another approach used Webb's NIR-SPEC micro-shutter assembly, the technology that allows simultaneous spectroscopy of 100 objects at once to confirm redshifts and basic properties for large samples of galaxies at redshift 7 and above, rather than relying on photometric estimates for statistical analyses. The spectroscopic samples confirmed the photometric trend. The excess was not a photometric artifact, and throughout this, the simulation teams were not idle. Groups running Illustris TNG and Eagle analyzed what the model predicted for the specific survey volumes and selection functions of Webb's observations, making the comparison as apples to apples as possible. In some cases, the simulations could marginally accommodate the observations with modified feedback parameters. In others, the discrepancy persisted at the multiple sigma level regardless of parameter choices. The community is in the position that observational science sometimes arrives at, confronting results that are real, reproducible, and not fully explainable by adjusting existing parameters. A position that calls for new ideas. While the broader statistical anomaly accumulated across Webb's various surveys, a parallel investigation was producing a different kind of discovery, not statistical excesses, individual records. The JADES program, the JWST Advanced Deep Extragalactic Survey, is one of the flagship observing programs in Webb's schedule. A collaboration of more than 80 astronomers from institutions across Europe and North America, JADES was designed not merely to image the early universe, but to characterize it in detail. To take the deep, spectroscopic measurements that turn a blurry smear of red light into a dataset with a known redshift, a measured star formation rate, and a chemical composition. JADES was designed to find and confirm the most distant galaxies Webb could detect. Its first major record came in late 2022. A galaxy designated JADES GS-Z130 was confirmed with a spectroscopic redshift of 13.2. In physical terms, this is the light we receive from a galaxy that was emitting it approximately 325 million years after the Big Bang. The universe was 1/14.2 its current size at that moment. That light has been traveling toward us ever since. At the time of confirmation, Jade's GS-Z13 Nil was the most distant galaxy ever spectroscopically verified, a galaxy observed when the universe was barely 2.4% of its current age. That record held for about 18 months. In early 2024, the JADES team identified a candidate that photometric analysis flagged as potentially more distant still. They scheduled Webb's near-infrared spectrograph to observe it, nearly 10 hours of observing time, accumulating every photon the ancient galaxy's light could offer over that period. 10 hours of Webb's time is a significant commitment. Observing campaigns are oversubscribed. The telescope is in constant demand from scientists around the world. These 10 hours represented a serious bet on this particular target. The bet paid off. The result, published in May 2024 in the journal Nature, established a new spectroscopic record, JADES GS-Z14-0, spectroscopic redshift 14.32. This places the observed galaxy approximately 290 million years after the Big Bang. Stop for a moment on that number. 290 million years. The Big Bang occurred 13.8 billion years ago. Webb is observing this galaxy when the universe was 290 million years old, about 2.1% of its current age. If you compressed all of cosmic history into a calendar year, this galaxy is being observed on January 7th. The universe at 290 million years was still in the deepest of its earliest epochs. The population 3 stars, the first generation, had barely had time to form, live out their brief lives of millions of years, and begin to die. The process of chemical enrichment was just beginning. The fog of the cosmic dark ages had only recently begun to clear under the ionizing radiation of the first stars and proto-galaxies, and what JADES GS-Z14-0 showed was not what a galaxy at that age should show. It was luminous, far more luminous than models predicted for a galaxy at that epoch. Its star formation rate, the rate at which it was converting gas into new stars, was high enough to produce the brightness Webb detected. Its physical size, approximately 1/600 light-years across, was also unexpected, small compared to the Milky Way's roughly 100,000 light-year diameter, but unexpectedly large for a galaxy observed only 290 million years after the Big Bang. Models of galaxy formation at this early epoch predicted compact, dense, proto-galactic clumps, not extended systems. JADES GS-Z14-0 was already more extended than models allowed. But those properties, striking as they were not the feature that caught the scientific community's attention most sharply. The spectrum contained oxygen. Think about that. Oxygen. In a galaxy that existed only 290 million years after the Big Bang. Oxygen does not come from the Big Bang. Hydrogen, helium, and trace lithium came from the Big Bang. That is all. Every other element, Every carbon atom in every living cell, every oxygen atom in every molecule of water, every iron atom in every human heart was made later inside stars. Oxygen, specifically element number 8, with its 8 protons, is synthesized in the cores of massive stars during the helium fusion phases that follow hydrogen exhaustion. When those massive stars die in supernovae or in direct collapse, they disperse that oxygen into the surrounding gas. The next generation of stars forms from enriched gas that now contains that oxygen. For Jade's GS-Z14 null to contain detectable oxygen at 290 million years, the following sequence must have occurred before the galaxy was even observed by Webb. At least one generation of massive stars must have formed from primordial hydrogen-helium gas. Those stars must have lived through their multi-million-year lifetimes. They must have died, dispersing oxygen into the surrounding interstellar medium. The enriched gas must then have been available for a new generation of star formation, the generation of stars we are actually detecting in Jade's GS-Z14-0. All of this before 290 million years. The first stars are thought to have begun forming between roughly 100 and 200 million years after the Big Bang. For an entire stellar generation to have formed, lived, and died, enriching the gas, and then for a second generation to have formed and been caught in active star formation by 290 million years is not strictly impossible. A very massive population 3 star might live only a few million years. In principle, the sequence can fit in the time available. But it is tight. Tight enough to push against the edges of current models. Tight enough that the presence of oxygen in Jade's GS-Z14-0 is not a curiosity, but a genuine scientific puzzle. Then, in 2026, Webb contributed a different kind of anomaly. Astronomers published observations of a massive galaxy that existed less than 2 billion years after the Big Bang. Older than Jade's GS-Z14-0, but still cosmologically young. And this galaxy, unlike the record breakers at extreme redshift, could be analyzed not just for what it contained, but for how it moved. The dynamical analysis came back with something unexpected. The galaxy showed essentially no rotation. This is strange. Galaxies acquire angular momentum during formation. The turbulent, rotating environment of a collapsing gas cloud naturally generates spin. And as the cloud collapses, that spin is conserved and amplified. Young, actively forming galaxies spin. The Milky Way rotates, carrying our solar system around its center at roughly 220 kilometers per second. Galaxies that have lost their rotation, that show the smooth, settled dynamics astronomers call dispersion-dominated, are typically the products of very long evolution. They have consumed their star-forming gas. They have experienced multiple mergers that disrupted and randomized stellar orbits. They have had billions of years for the ordered motion of a disk to dissolve into the quasi-random motion of an elliptical. In the local universe, this behavior belongs to the most massive, most evolved elliptical galaxies, objects that have been assembling for essentially the entire history of the cosmos. Finding this in a galaxy less than 2 billion years old means that whatever processes normally take many billions of years, complete gas consumption, dynamical relaxation, the quenching of star formation, had completed in a fraction of the time. Each of these discoveries taken alone might be explained by adjusting a model parameter, but together they form a pattern that points in a single direction. The early universe looks more evolved than it should. There is something important to say about what more evolved means here, because it is easy to misread the situation. We are not saying the universe is older than we thought. The age of the universe, 13.8 billion years, is one of the most robustly constrained numbers in all of science. Multiple independent measurements using completely different physical phenomena agree on it to a level of precision that leaves little room for doubt. What we are saying is something different. We are saying that within the time the universe has had, 290 million years, 700 million years, 2 billion years, the processes of structure formation apparently ran faster than the standard model allows, that galaxies assembled more mass earlier, that chemical enrichment proceeded through stellar generations at a pace the standard picture doesn't naturally account for, that the transformation from a young, turbulent, star-forming system to a settled, quenched, rotationally smooth one apparently happens on timescales far shorter than what we observe in the local universe. The early universe had the same age as the standard model says. It just did more with that time than we predicted. And that distinction between the universe being older and the universe being more efficient points towards specific physics. The efficiency of processes depends on physical conditions. The conditions of the early universe were different in ways we can calculate, but the calculations run through the standard model don't produce this level of efficiency. Something in the conditions or in the physics that governs what those conditions do is not correctly captured. That is the puzzle Webb has crystallized. While Webb was quietly dismantling expectations about the early universe, a separate problem, one that had been building for years before Webb even launched, was coming to a head. The Hubble constant. Named for Edwin Hubble, the astronomer who established in the 1920s that the faint, spiral nebulae scattered across the sky were not clouds of gas within our galaxy, but entire separate galaxies, and who discovered in that same work that those galaxies were receding from us. Their light shifted toward the red by their motion through expanding space. The Hubble constant is the number that describes how fast the universe is growing. Written as h0, its value tells you how many kilometers per second faster a distant galaxy appears to be receding for each additional megaparsec of distance. 1 megaparsec is approximately 3.26 million light-years. A Hubble constant of 70 kilometers per second per megaparsec means a galaxy 10 megaparsecs away recedes at 700 kilometers per second, and 100 megaparsecs away at 7,000 kilometers per second. This number sets the age of the universe. It sets the size of the observable universe. It connects dark energy's strength to the universe's measured expansion. It is the most fundamental single number in observational cosmology. For much of the 20th century, Measuring it accurately was the great unsolved problem in the field. Serious estimates from serious astronomers ranged from 50 to 100 kilometers per second per megaparsec. A factor of 2 uncertainty in the universe's expansion rate and therefore its age. For a field that prides itself on precision, that was an embarrassment. The Hubble Space Telescope was specifically tasked with resolving this. One of the primary science goals of the Space Telescope, named after Edwin Hubble, was to measure his constant to better than 10%, to use Cepheid variable stars in nearby galaxies to build the distance ladder that would carry measurement out to the distances where galaxy recession velocities give a clean, uncontaminated reading. By the 2000s, that mission had largely succeeded. The key project team announced a value of 72 kilometers per second per megaparsec, with an uncertainty of about 10%. The factor of 2 debate was over, and then the measurements kept improving. The uncertainties shrank, and something emerged from the improved precision that no one had expected. 2 methods of measuring the Hubble constant were giving different answers. The first method starts from the early universe. The cosmic microwave background carries within it the imprints of acoustic oscillations, pressure waves that propagated through the hot plasma of the early universe before recombination, when everything was a dense soup of particles and sound waves could travel through the cosmos at a substantial fraction of the speed of light. These waves left a characteristic scale imprinted in the CMB's temperature fluctuations, a scale related to how far sound could travel before recombination froze the pattern in place. By measuring this scale and the full power spectrum of CMB fluctuations, cosmologists can determine the universe's composition, geometry, and early expansion rate with extraordinary precision. The Planck satellite, which mapped the CMB at full sky coverage from 2009 to 2013, produced from this analysis a Hubble constant of 67.4 kilometers per second per megaparsec, with an uncertainty of less than 0.5%. The second method works in the opposite direction, measuring the expansion rate directly using objects whose distances are independently known. The foundation of this approach is Cepheid variable stars. Cepheids pulse with regular periods. They expand and contract, brightening and dimming in cycles of days to months. In 1912, Henrietta Swan Leavitt, working at the Harvard College Observatory under conditions in which women were employed primarily as human computers to catalogue stellar observations, discovered a precise relationship among Cepheids in the small Magellanic Cloud. More intrinsically luminous Cepheids pulsed more slowly. Period perfectly correlated with luminosity. This is one of the most consequential discoveries in the history of astronomy. Measure a Cepheid's pulsation period and you know exactly how intrinsically bright it is. Compare that intrinsic brightness to how bright it appears from Earth, and the inverse square law of light tells you the distance. No models required, no assumptions about the galaxy's nature, a direct measurement. By calibrating Cepheid distances to nearby galaxies then using those galaxies as anchors to extend to galaxies far enough away that their recession velocities give a clean Hubble constant measurement, astronomers built a distance ladder spanning billions of light years. The SHOES collaboration, Supernova HO for the equation of state, led by Adam Rees at Johns Hopkins University, had been building this ladder with increasing precision for more than 2 decades, using the Hubble Space Telescope to measure Cepheids in galaxies that had also hosted Type Ia supernovae. Another standard candle, useful at even greater distances. The team converged on a Hubble constant of 73.0 kilometers per second per megaparsec, with an uncertainty of about 1%. Type Ia supernovae deserve a brief mention because they add an independent rung to the ladder. These are thermonuclear explosions of white dwarf stars in binary systems. A white dwarf accretes matter from a companion until it reaches a critical mass, roughly 1.4 times the mass of our Sun, and then ignites in an explosion that briefly outshines an entire galaxy. Because the explosion trigger mass is predictable, these supernovae have a relatively standard peak brightness, and because they are enormously luminous, they can be observed at distances far beyond where Cepheids can be individually resolved. Type Ia supernovae extend the distance ladder by another factor of hundreds, reaching out into the regime where galaxy recession velocities give a direct, clean measurement of the Hubble constant. In 1998, it was Type Ia supernovae that revealed the universe's accelerating expansion. The SHOES approach linked Cepheid distances to the supernovae and the supernovae to the Hubble constant. Other teams, using different intermediate rungs, including the tip of the red giant branch, a different stellar distance indicator that uses the brightest stars at the moment of helium ignition in stellar cores, a transition that occurs at a highly predictable intrinsic luminosity, arrived at local Hubble constant values consistently in the range of 71 to 74, all higher than the CMB's 67.4, 67.4, 73.0, a difference of about 5.6 kilometers per second per megaparsec, a fraction of roughly 9%. At the precision of both measurements, the gap between them exceeded 5 standard deviations, 5 sigma. In particle physics, 5 sigma is the threshold for declaring a discovery. Here, it was the threshold of a disagreement. For years, the most natural explanation was that the distance ladder had a systematic error. The environments in which Cepheids live, star-forming regions near the cores of distant galaxies, are crowded. Multiple stars can fall within a single Hubble image pixel, blending their light together. If Cepheids appeared brighter than they really were because of this blending, they would appear closer than they really were, and the derived Hubble constant would be inflated. Webb was uniquely positioned to test this. With its superior angular resolution at infrared wavelengths, Webb could separate stars in crowded fields that Hubble could not resolve. It could observe the same Cepheids the SHOES program had measured and check directly for blending bias. The SHOES team used Webb to observe Cepheids in several key calibrator galaxies in 2024 and 2025, applying every available correction. They checked for crowding, They verified the period luminosity relation. They examined every potential source of systematic error that had been proposed in the literature. The Cepheid measurements held. Webb found no significant crowding bias. The Hubble-derived distances were not inflated. The local expansion rate of 73.0 was confirmed. The gap with the CMB's 67.4 remained exactly where it had been. The Johns Hopkins team stated the conclusion directly. With the primary proposed systematic error investigated and eliminated by Webb's improved resolution, what remains is a genuine and significant discrepancy between two independent measurements of the same fundamental constant. The universe is expanding faster than the standard model, calibrated on the ancient cosmic microwave background, predicts it should be today. The implications of this are worth dwelling on. If the Hubble tension is real, if it represents genuine physics rather than measurement error, then something happened between the epoch of the CMB, some 380,000 years after the Big Bang, and today. Something that caused the expansion to be faster than the model initialized at the CMB epoch predicts. Something that the 13.8 billion years of cosmic evolution between then and now has produced or maintained or amplified that the standard model does not account for. What that something could be covers a range of theoretical territory. It could be that dark energy is not constant, but has evolved over time, stronger in the recent past than in the early universe. The DSI results published in 2025 showing hints of dark energy variation are provocative in this context, though not yet definitive. It could be that there is an additional component of energy in the universe that the standard model simply hasn't included. A new particle species, a new field, something that exerts just enough influence on the expansion rate at late times to explain the gap. It could be that our understanding of how Cepheids work contains a systematic error so subtle that neither Hubble nor Webb can find it. This is the most conservative possibility, and it is the one that becomes less plausible with every additional cross-check that holds. Or it could be that the standard model is missing something more fundamental, a component of physics that is present throughout cosmic history, but that manifests differently at the CMB epoch, and today in ways that prevent the two epochs' measurements from agreeing even when the model is correct in every other respect. Two separate anomalies, two independent lines of evidence, both pointing toward the same conclusion. Something in the standard picture is missing. Faced with the galaxy anomalies and the Hubble tension, theorists have not been standing still. A wide variety of proposals have been advanced, developed, refined, and in some cases partially abandoned over the years since these problems sharpened into focus. Each proposal captures part of the picture. None captures all of it, and the failure of any single modification to simultaneously resolve all of the anomalies is itself informative. It suggests the missing ingredient may be more than a single parameter adjustment. The most studied modifications to the dark matter side of lambda CDM focus on the thermal properties of the dark matter particle. In the standard model, dark matter is cold, meaning the particles have velocities much smaller than the speed of light during the epoch when cosmic structure forms. Cold particles can cluster on arbitrarily small scales. They settle into halos of all sizes, from galaxy-sized down to subgalactic, and the smallest of these halos should be enormously numerous. The Milky Way alone should be surrounded by many thousands of small dark matter subhalos. But if dark matter particles are slightly warmer, if they have higher random velocities, they will free stream through space and erase density fluctuations below a certain scale. Below roughly a few kiloparsecs, warm dark matter halos simply fail to form. The smallest scales are smoothed out. The first collapsed structures are somewhat larger. This is warm dark matter, and it would change the early universe in ways that might ease some of the tension with the observed galaxy population. If the earliest halos are somewhat larger, gas falling into them might form stars in a way that more easily produces the more massive than expected systems Webb is finding. An even more exotic possibility is fuzzy dark matter, a dark matter candidate consisting of an extremely light boson, perhaps 10 to the negative 22 electron volts in mass, roughly 30 orders of magnitude lighter than the electron. At such extraordinarily small mass, the de Broglie wavelength of the particle, the scale below which quantum wave behavior dominates over classical particle behavior, is comparable to the size of individual dwarf galaxies. The quantum nature of fuzzy dark matter would create wave-like interference patterns in the density field, preventing the formation of structures below a certain scale in ways that differ from warm dark matter's simple smoothing. Neither warm nor fuzzy dark matter has been confirmed or definitively ruled out. Observational constraints come from multiple directions: the Lyman alpha forest, counts of satellite dwarf galaxies around the Milky Way, and Andromeda, the internal density profiles of individual galaxies. Current data allows some range of parameter space for warm dark matter, but strongly constrains the most extreme versions. And here is the important subtlety that makes dark matter modifications complicated as a solution to Webb's anomalies. Modifying dark matter changes when and how efficiently dark matter halos form, but the mass of stars that form within those halos still depends on the baryonic physics, the rate at which gas cools and collapses, and the rate at which stellar feedback expels gas. A warm dark matter halo might form slightly differently or slightly earlier than a cold dark matter halo, but you still need to convert that halo's gas into stars. The star formation efficiency problem, the need for near-total conversion of gas to stars in some of the most extreme candidates, is not obviously solved by changing the dark matter thermal properties. The two problems are coupled but not identical. A complete solution needs to address both. A different class of solutions focuses on dark energy rather than dark matter, specifically on whether dark energy has always been exactly what it is today. The Standard Model treats dark energy as a cosmological constant, a fixed energy density of empty space, the same everywhere, the same at every moment in cosmic history. But this assumption is a choice, not a derivation. It can be relaxed. If dark energy varied over time, if there was an additional dark energy-like component present in the early universe, one that had meaningful energy density around the epoch of recombination and then decayed away, the early expansion history would differ from the Standard Model's prediction. The acoustic scale imprinted in the CMB would be slightly different, and the Hubble constant inferred from CMB measurements, which depends on this scale, would be slightly higher, potentially bringing it into better agreement with the local measurement. This hypothesis, called early dark energy, was developed in detail by Vivian Paulin and colleagues in a 2019 paper. The idea generated enormous interest, and initial analyses showed it could substantially reduce the Hubble tension. But careful testing revealed a problem. Adjusting early dark energy to reduce the Hubble tension tends to worsen the model's fit to other measurements, specifically to the detailed shape of CMB fluctuations on small angular scales, as measured by the Atacama Cosmology Telescope and the South Pole Telescope at higher angular resolution than Planck. These experiments place constraints that squeeze early dark energy's parameter space. The model remains viable, but under pressure. Recent results from the Dark Energy Spectroscopic Instrument, DESI, a survey instrument on the Mile Telescope at Kitt Peak National Observatory in Arizona, added another thread. DESI measured the baryon acoustic oscillation scale in galaxy distributions across a range of cosmic epochs, and the early results suggested hints that dark energy's strength may have varied over cosmic time. Preliminary results released in early 2025 showed tantalizing deviations from a pure cosmological constant. The deviations are not yet statistically definitive, and more data is needed, but they point toward the same general direction as early dark energy, toward a dark energy that is not simply a fixed constant of nature. There are also proposals that work within the standard cosmological framework, but argue that the galaxy formation physics encoded in current simulations is wrong. Not the cosmology, but the astrophysics. Stellar feedback is the collective name for the processes by which stars push back against the gas, trying to form more stars. Young, massive stars emit intense ultraviolet radiation that ionizes and heats surrounding gas, preventing further collapse. Supernovae inject kinetic energy and momentum into the interstellar medium, driving outflows that remove gas from the galaxy. Accreting black holes, AGN, launch jets and winds that heat the gas in the entire halo, shutting off the supply of fresh material that galaxies need to keep forming stars. These processes are crucial to galaxy formation. Without feedback, simulations produce galaxies far too massive. All the gas collapses into stars, and galaxies end up many times more massive than observed. Feedback regulates star formation, keeping it at the few percent efficiency we measure today. Some theorists argue that in the very early universe, in the first few 100 million years, in proto-galactic systems far smaller and denser than anything that exists today, feedback may have operated differently. The gravitational potential wells were shallower, the systems were more compact, the radiation fields were stronger. In these conditions, perhaps feedback was suppressed in ways that current simulations, calibrated on today's galaxy population, fail to capture. If early feedback was suppressed, gas could collapse more efficiently, star formation rates could be higher, galaxies could assemble stellar mass faster. This explanation is appealing because it requires no new fundamental physics, only a revision of the applied astrophysics in a regime we have never before been able to observe. But the degree of efficiency required by some of the anomalous galaxies that survive AGN scrutiny still exceeds what any physically motivated suppressed feedback model has been able to produce. You can make star formation more efficient. You cannot make it that much more efficient, given what we understand about stellar physics. The theoretical situation, honestly assessed, is this. There are many proposals. Some are clever. Some may be partially correct. None of them resolves the galaxy anomalies and the Hubble tension simultaneously, cleanly, without introducing new tensions elsewhere. And when independent anomalies accumulate, each individually arguable, but collectively pointing in the same direction and collectively resisting any single proposed fix. The question that serious scientists begin to ask is not which parameter we got wrong. It is whether the framework itself is complete. Roger Penrose won the Nobel Prize in Physics in 2020. He shared it with Andrea Ghez of UCLA and Reinhard Genzel of the Max Planck Institute for Extraterrestrial Physics. Ghez and Genzel received their share for their discovery through decades of precise stellar tracking of a compact, supermassive object at the center of the Milky Way. The object we now confirm is Sagittarius A, a black hole of 4 million solar masses, whose gravitational influence on nearby orbiting stars provides some of the most direct evidence for the existence of black holes ever gathered. Penrose's portion of the prize was for work done in 1965, a mathematical proof published in Physical Review Letters that if general relativity is correct and if matter satisfies reasonable energy conditions, conditions that all known forms of matter satisfy in all tested physical regimes, then singularities must inevitably form inside black holes, regions of infinite density where the known laws of physics break down. This was not a welcome result in 1965. The physics community preferred general relativity to remain well-behaved everywhere, and many hoped that the equations, when applied to the extreme conditions inside a collapsing star, would somehow find a way around the singularity. Penrose showed, rigorously, using the new mathematical framework of global methods in differential geometry, that they could not. The singularity was not a quirk of a particular solution, it was a theorem, following necessarily from the structure of general relativity itself. It took years to gain full acceptance. Eventually it did. Penrose has been developing a different theory for roughly 20 years, and the physics community has been considerably slower to accept it. Because this theory does not prove something about the interior of black holes, which can in principle be confirmed by finding black holes that behave as the theorem predicts. This theory makes claims about the entire history of the cosmos, and about things that happened before the observable universe came into existence. He calls it conformal cyclic cosmology. The motivation begins with one of the deepest unresolved puzzles in theoretical physics, the problem of the initial entropy of the universe. The second law of thermodynamics is among the most fundamental laws of nature. In a closed system, entropy, the measure of disorder, of the number of accessible microscopic arrangements consistent with the system's macroscopic state, never decreases. Things fall apart. Heat dissipates from hot to cold and not spontaneously from cold to hot. Cream mixes into coffee. The direction of time is, in a deep sense, the direction in which entropy increases. The Big Bang produced a universe of extraordinarily low entropy. Think about what this means. The cosmic microwave background, which maps the state of the universe at 380,000 years, shows temperature variations of roughly 1 part in 100,000. The early universe was almost perfectly smooth, almost perfectly uniform. And this is, from the perspective of thermodynamics, a state of low entropy, particularly with respect to gravity. Without gravity, a uniform gas is actually high entropy, random disorder. But gravity is different. Gravity is attractive. For a system governed by gravity, the high entropy state is not uniform distribution, but maximal clumping. All the matter gathered into one place, in one object, in a black hole. A smooth, uniform distribution of matter in a gravitating system is, paradoxically, a state of extremely low gravitational entropy. The universe has been climbing away from this low entropy state ever since, forming galaxies, then stars, then black holes, steadily increasing its gravitational entropy. Why did the universe begin in such a low entropy state? The inflationary model, developed by Alan Guth in 1980, refined by Andrei Linde and others, proposes that in the first tiny fractions of a second, the universe underwent a brief period of exponentially rapid expansion. A patch far smaller than an atomic nucleus inflated to a scale larger than what we can observe today. This expansion stretched any initial irregularities to scales larger than the observable universe, erasing them, leaving behind the almost perfectly smooth cosmos that the CMB reveals. Inflation explains the smoothness beautifully. The CMB's measured fluctuations are consistent with the quantum fluctuations that inflation predicts would survive this stretching. The model has significant observational support, but Penrose finds it incomplete as a fundamental answer. Because inflation itself requires an initial state, the inflaton field must be in a specific configuration to produce inflation rather than something else. That configuration represents order, low entropy, in the pre-inflationary universe. You have not explained why entropy was low at the beginning. You have moved the question back one step. Why was the inflaton field in the right configuration? Penrose has calculated, using Boltzmann's statistical mechanics and asking what fraction of all possible initial configurations would produce a universe with the low entropy we observe, a probability so vanishingly small that writing it in decimal form would require placing a decimal point followed by more than 100 zeros before reaching the first significant digit. A number that has no physical intuition attached to it. A number that says, this did not happen by chance. The initial low entropy of the universe demands an explanation. Inflation provides a mechanism, but not a reason. Penrose's framework provides both. His own answer approaches the problem from the other end of time. The far future of the universe is, in principle, calculable. Stars consume their fuel and die. The last stellar remnants, white dwarfs, neutron stars, slowly cool over incomprehensibly long timescales. Protons, If they decay, as most extensions of the Standard Model suggest they should, will do so on timescales of perhaps 10 to the 34th power years or more, timescales expressed in numbers that have no physical intuition attached to them. Black holes evaporate. This is the Hawking radiation process, predicted theoretically in 1974. Quantum mechanics near the event horizon causes pairs of particles to spontaneously appear, with one particle falling into the black hole and the other escaping. The escaping particle carries energy, and slowly, over time, the black hole loses mass. For a black hole of the mass of the Sun, complete evaporation takes approximately 2 times 10 to the 67th years. For a supermassive black hole of 1 billion solar masses, common at the centers of galaxies, the timescale is roughly 10 to the 83rd years. These numbers are so large that writing them in full requires counting zeros in batches, but given enough time, every black hole evaporates. And before the last black holes finish their evaporation, all ordinary matter, if proton decay occurs, will have long since ceased to exist. The universe in the extraordinarily distant future contains, eventually, nothing but radiation. The remnants of Hawking evaporation, photons and other massless particles propagating through an ever-expanding void. Here is where Penrose's insight becomes precise and strange. Massless particles, photons, do not experience time in the way that massive particles do. In the framework of special relativity, a photon moving at the speed of light accumulates 0 proper time along its world line. The photon that left the Sun 8 minutes ago has, from its own reference frame, not experienced any time at all. For a massless particle, the distinction between past and future loses its usual meaning. More concretely, without massive particles, there is no physical system that can serve as a clock. Every timekeeping device, every oscillation, every orbit, every atomic transition depends on mass. In a universe containing only massless radiation, the passage of time becomes physically unmeasurable. Without massive particles, there is also no concept of absolute length. All length standards ultimately rest on the properties of atoms and their constituent particles, which require mass. In a universe of pure radiation, absolute scale vanishes. Without time and without scale, the only geometrically meaningful structure that remains is the angular structure of causal relationships, which directions events are in relative to each other, how events relate in terms of the light cones that connect them. Mathematicians call this conformal structure. Penrose's central mathematical claim is this: a universe that has aged into a state of pure, massless radiation, vast, cold, expanding forever, containing nothing but the remains of Hawking evaporation, is, in its conformal structure, exactly equivalent to the initial state of a new Big Bang, not approximately equivalent, not physically similar. Conformally equivalent in the precise mathematical sense. The future of a dying universe and the birth of a new one are, in the only geometric sense that remains meaningful when mass disappears, the same configuration. The end of one eon is the beginning of the next, not through any catastrophic event, not through a bounce or a collision or an explosion, through the mathematics of what it means to lose all massive particles. The transition is seamless, built into the structure of the theory. And the low entropy of our Big Bang, the smoothness of the early universe that inflation addresses but does not, in Penrose's view, ultimately explain, is guaranteed by this transition. Every eon begins smooth because the conformal matching of the end of the previous eon to the beginning of the next one produces a smooth initial state, not as a special initial condition, as a mathematical consequence. Is this correct? The honest answer is, we don't know, and that is a carefully chosen formulation, not a hedge. CCC is mathematically sophisticated. Penrose published a full book on the framework in 2010, laying out the mathematics in detail. But the theory faces real objections. The conformal rescaling that makes the transition work involves specific choices about how physical laws transform across the boundary, and different choices give different results. The framework's reliance on the eventual disappearance of all massive particles through proton decay and Hawking radiation is conjectural. Proton decay has not been observed in any experiment, and some theoretical frameworks allow protons to be stable. The connection between the conformal boundary and the actual physical state of a new universe requires assumptions that not all physicists accept. But CCC makes specific predictions that can, in principle, be tested. In the previous eon, the last massive objects were supermassive black holes, evaporating slowly through Hawking radiation over timescales of 10 to the 80th or 90th years. In the aeon before ours, the mergers of these final supermassive black holes would have released gravitational radiation, gravitational waves, in events of enormous energy. Those gravitational waves propagating through the final era of the previous aeon would leave an imprint on the conformal boundary that our universe inherited. In our CMB, this imprint would appear as concentric circular patterns of anomalous temperature variation, centered on the sky positions corresponding to where those ancient black hole mergers occurred in the previous eon. Separately, the thermal radiation from the final evaporation of the last black holes in the previous aeon, Hawking radiation, would leave bright spots in the CMB. Approximately Gaussian features of characteristic angular size that Penrose calls Hawking points. In 2018, Penrose, working with Daniel An and Krzysztof Meissner, published an analysis of Planck satellite CMB data. They identified anomalous bright spots in the Planck CMB temperature maps that they claimed were statistically consistent with what Hawking points from a previous aeon would look like. The paper was peer-reviewed and published. The statistics were explicit and checkable. The reaction was skeptical but not dismissive. Several groups performed independent analyses of the same Planck data and of simulated CMB maps generated by standard inflationary cosmological models. Their conclusion was that the claimed bright spots were not statistically distinguishable from features that arise by chance in a standard realization of the inflationary CMB, that the evidence did not rise to the threshold required for a claimed detection of non-standard physics. The 2018 claim was not refuted in the sense of being shown false. It was challenged on statistical grounds. The debate about how best to test for such a signal in the CMB is itself ongoing. The challenge is genuinely difficult, and it is worth understanding why. If you search a dataset for a specific kind of feature, bright spots of a certain angular size and profile, you will find some, even in a random dataset, simply by chance. The question is, Deleuze, whether you find more of them than chance predicts, and at higher significance than chance allows. But how you define the feature, how you calculate the probability of finding it by chance, and what statistical test you use to assess significance, all of these choices affect the conclusion. Penrose's team made one set of choices. Critics made other choices. The results differed. This is not unusual in complex statistical analyses of noisy data. It is, in fact, the normal process by which contested observational claims are tested, but it means the debate is not over. What would settle it is a new CMB map with higher sensitivity, specifically the sensitivity to distinguish the subtle temperature signatures of Hawking points, if they exist, from the intrinsic fluctuations of the standard inflationary CMB. The Simons Observatory, under construction in Chile, and the proposed CMB-S4 experiment, designed with an order of magnitude more sensitivity than Planck at certain angular scales, would provide data capable of testing Penrose's prediction more definitively than any existing instrument can. In 2025, a new paper returned to CCC examining the full mathematical framework and the objections that had accumulated over 15 years of debate. The conclusion was measured. The framework is more internally consistent than many of its critics have argued. The objections are challenges rather than fatal flaws, and the observational signatures CCC predicts for the CMB are genuinely different in character from purely inflationary predictions given sufficient observational precision. And the paper noted, as several researchers had begun to note, what was accumulating in the background of this entire discussion: the James Webb Space Telescope anomalies. This connection must be stated carefully because it is exactly the kind of suggestive juxtaposition that can be overstated. CCC does not specifically predict that early galaxies should be anomalously massive. It does not predict the oxygen signature in JADE's GS Z14-0. Penrose did not develop the theory with Webb's observations in mind. He has not claimed that Webb confirms CCC, but CCC does propose that the beginning of our universe carried imprints of the previous eon structure. The distribution of supermassive black holes in the previous eon, their merger history, the pattern of Hawking radiation from their final evaporation, all of this would leave imprints on the conformal boundary that shaped the initial conditions of our eon. If those initial conditions were shaped not only by quantum fluctuations during inflation but also by the structural inheritance from a previous cosmic cycle, the resulting distribution of matter in the very earliest times might differ from what a purely inflationary scenario predicts. Different, in ways that could, in principle, produce more and more massive structures earlier than standard models allow. That is speculative, genuinely speculative in the scientific sense of a coherent theoretical possibility not yet connected by specific mathematical predictions to specific observational signatures, not hand-waving, but not an explanation either. What is not speculative is the broader situation the theory now finds itself in. A framework that spent 20 years at the margins of mainstream cosmology, developed by a physicist who had already been proven right after decades of resistance, for a proof that the mainstream initially found uncomfortable, finds itself in a scientific landscape that has become unexpectedly less settled. A landscape in which the early universe looks more evolved than it should, in which the expansion rate of the cosmos stubbornly refuses to reconcile two of its measurements, in which the Standard Models framework is confirmed and anomalous simultaneously. The anomalies do not prove CCC. They widen the aperture of what the community is required to consider, and in science, that is how paradigm shifts tend to begin, not with a single dramatic refutation of the old theory, but with anomaly after anomaly accumulating, each one individually arguable, collectively undeniable, until the weight of what the existing framework cannot explain becomes heavier than the discomfort of asking whether something deeper is required. We are at an unusual moment in cosmological history. Lambda CDM has been the reigning framework for more than 6 decades. It was assembled piece by piece, general relativity, verified in observation after observation since Eddington's eclipse expedition of 1919, the discovery of the cosmic microwave background in 1965 by Penzias and Wilson, who initially thought the persistent microwave signal was pigeon droppings in their antenna, the mapping of large-scale cosmic structure into its filamentary web through galaxy surveys in the 1980s and 1990s, the discovery of dark energy's acceleration by 2 independent teams in 1998, a result so counterintuitive that Saul Perlmutter and Brian Schmidt, the leaders of those teams, spent years verifying it before publishing. The high-precision mapping of the CMB by WMAP, and then Planck through the 2000s and 2010s. Each edition extended the model's explanatory power. Each test it passed made the framework more secure. By the time James Webb launched, Lambda CDM felt mature in a particular sense. Not final, physicists are careful about claiming final theories, but stable. The major cosmological parameters were known to percent-level precision. The model's predictions for the large-scale structure of the universe, for the primordial element abundances, for the CMB power spectrum, all of these were not merely confirmed, but confirmed at levels of precision that would have seemed extraordinary to cosmologists of the 1970s. James Webb Space Telescope has changed the texture of this situation. Not through a single dramatic falsification. There is no single Webb result that definitively breaks the model. The model still works for the large-scale structure of the universe. It still correctly predicts the CMB fluctuations. It still correctly accounts for the primordial hydrogen and helium ratios. These pillars of the framework are not shaken. But in the specific regime that Webb was designed to probe, the universe at its earliest epochs, the galaxy populations at redshifts above 7, the most ancient light detectable, the framework's predictions are consistently wrong in a consistent direction. Consider the full picture. Webb looks at the deepest, oldest portions of the sky and finds galaxies too massive for what the model predicts at that epoch. After careful verification eliminates the most extreme candidates as AGN, a statistically significant excess of massive early galaxies remains. Different telescopes, Different instruments, different sky fields, different teams, all finding the same excess. Webb's most distant spectroscopic confirmation, JADES GS Z140, redshift 14.32, age 290 million years, shows oxygen in its spectrum. Oxygen that requires prior stellar generations to produce, in a universe less than 300 million years old. A galaxy less than 2 billion years old shows dynamical signatures of a fully quenched, rotationally settled system. Behavior that in the local universe belongs to the oldest, most evolved elliptical galaxies, systems that have been assembling for the entire history of the cosmos. And separately, Webb's measurement of Cepheid variable stars confirms the Hubble tension. The universe's expansion rate measured locally disagrees with the rate predicted by the early universe CMB measurement at a level of 5 standard deviations, a discrepancy that Webb's superior resolution has now verified is not a measurement artifact. These anomalies are not a crisis. That word implies a breakdown that has already happened, a catastrophic failure. What is happening is more subtle than that. What is happening is a pressure, the accumulation of evidence that the framework, while correct in many of its predictions, is not complete in the specific regime Webb has now made accessible. The history of physics is, in one reading, a history of this kind of pressure. Newton's laws worked for more than 2 centuries with extraordinary success. They described the orbits of planets, the trajectories of cannonballs, the behavior of fluids, the stresses in bridges, brilliantly, dependably, across an enormous range of conditions. And then, at the edges of what Newton could describe, at velocities approaching the speed of light in strong gravitational fields near massive objects, small but real discrepancies appeared. The precession of Mercury's perihelion, the bending of starlight by the sun. These anomalies did not break Newton's laws for everyday applications, but they indicated that Newton's laws were a limiting case, valid in a particular regime, not the complete description of reality. Einstein's general relativity contained Newton's laws as a special case, correct when velocities are small compared to light and gravitational fields are weak. But general relativity was the larger framework, applying in the regimes where Newton failed. The same pattern appeared in thermodynamics and electromagnetism. Classical physics described heated objects as emitting radiation according to classical predictions. The prediction was precise, and it was catastrophically wrong at short wavelengths, predicting infinite energy emission, what came to be called the ultraviolet catastrophe. The resolution was Planck's quantization of energy, the beginning of quantum mechanics, a framework that classical physics was entirely unprepared for. Quantum mechanics did not destroy Maxwell's equations. It revealed that Maxwell's equations were a limit of a deeper theory. Each revolution in physics produced a larger framework that contained the previous one. Newton's laws emerge from general relativity in the appropriate limit. Classical electrodynamics emerges from quantum electrodynamics. There is also a more recent precedent, closer to home. The standard model of particle physics, which describes the quarks and leptons and force-carrying bosons that make up everything we can detect, has been extraordinarily successful. It predicted the existence of the Higgs boson, confirmed in 2012 at the Large Hadron Collider. It predicts the anomalous magnetic moment of the electron to 11 decimal places, matching experiment with a precision that has no parallel in the history of science. It works. And yet physicists know it is incomplete. It does not include gravity, it requires the values of its parameters, the masses of particles, the strengths of forces, to be specified from observation rather than derived from first principles. It says nothing about dark matter, which is real, whose gravitational effects are extensively documented and which it cannot account for. Every physicist working in fundamental physics today assumes the standard model of particle physics is a limit of a larger, not yet discovered framework. Lambda CDM may be in the same position. What contains lambda CDM as a limit valid in certain regimes, emerging from some deeper framework in the domain where its predictions hold, is the question that James Webb Space Telescope has transformed from theoretical speculation into observational urgency. The next generation of instruments will push this further. The Nancy Grace Roman Space Telescope, when it launches and begins operations, will carry the same mirror diameter as Hubble, 2.4 meters, but a field of view 100 times larger than Hubble's cameras. In a single exposure, Roman will image an area of sky that would take Hubble months to cover. Over its survey period, it will catalogue hundreds of millions of distant galaxies, building the statistical samples that Webb's deep but narrow observations cannot provide. If the excess of massive early galaxies is real and significant, Roman will quantify it with a precision that will be very difficult to explain away. The Vera C. Rubin Observatory on Cerro Pachon in the Chilean Andes has begun its legacy survey of space and time, a 10-year program of repeatedly imaging the entire southern sky in 6 filters, building a catalogue of tens of billions of astronomical objects. Its contributions to the Hubble tension debate will come from independent measurements of weak gravitational lensing and galaxy clustering, probing the matter distribution of the universe in ways complementary to both the CMB and the distance ladder. The Square Kilometre Array, a network of radio dishes under construction in South Africa and Australia, forming an effective collecting area of 1 square kilometre, will observe hydrogen gas in emission at radio wavelengths across cosmic history, directly mapping the neutral hydrogen content of galaxies from the epoch of Ryanization to the present day. It will probe the transition from the cosmic dark ages to the era of the first stars and galaxies, in a regime where optical and infrared telescopes cannot operate. Future CMB experiments. The Simons Observatory, already under construction in the Chilean Atacama Desert, and the proposed CMB S4 experiment will measure the CMB temperature and polarization power spectra at sensitivities an order of magnitude beyond what Planck achieved. These measurements will either further constrain early dark energy models and sharpen the Hubble tension, or reveal in the CMB's detailed structure the signatures that theories like conformal cyclic cosmology predict. The extremely large telescope under construction on Cerro Armazones in Chile will be the world's largest optical and infrared telescope when it achieves first light, a 39-meter primary mirror larger than any ground-based telescope ever built. It will be capable of obtaining spectra of extremely faint galaxies that Webb images but cannot spectroscopically characterize. The combined power of Webb in space and the ELT on the ground will make the first billion years of cosmic history the most intensively studied epoch in observational cosmology within the next decade. There is something that deserves to be said about what all these instruments will collectively make possible, beyond their individual contributions to specific questions. For most of human history, cosmology was a theoretical discipline. The universe's earliest epochs were inaccessible to direct observation. The first 100 million years, the Dark Ages, the cosmic dawn, the ignition of the first stars, existed only in equations and simulations. We could check our models against observations of the universe at intermediate ages, where Hubble could reach and extrapolate backward. But the extrapolation was necessarily an act of faith in the theory. Webb changed this. For the first time in history, the cosmic dawn is accessible to direct measurement. The first galaxies are not theoretical constructs but observed objects with measured redshifts and spectral features and chemical compositions. They can be compared against model predictions, not just qualitatively but quantitatively, specifically falsifiably. And the Roman Rubin, SKA, ELT, and next-generation CMB experiments will extend this regime further, filling in the observational picture with statistics and precision that no single telescope can provide. Within a decade or two, the first billion years of cosmic history, which was almost entirely dark in observational terms as recently as 2020, will be the best mapped epoch in all of cosmology. That is a remarkable thing to be alive for. And if the anomalies persist under all of this scrutiny, if the massive early galaxies, the early chemical enrichment, the Hubble tension, all hold up across all the cross-checks that multiple generations of new instruments will provide, then we will have in hand the most important scientific result of this century. Not the confirmation of the standard model, the first confirmed signal that something lies beyond it, and the theoretical community is producing new simulations. The computational resources available today allow simulations with higher resolution, more realistic treatment of feedback physics, and larger simulated volumes simultaneously. Some of Webb's most surprising findings are being studied in detail, with specialized simulations that push stellar feedback modeling to its limits. The work is ongoing, active, and, to those involved in it, genuinely exciting. Because this is what science actually looks like when it is working well. Not the confident confirmation of a perfect theory, something more interesting. A conversation with a universe that keeps saying, "The picture you have is good. It is not complete. Keep looking. We are looking." The telescope, 1,000,000 miles from Earth, is still watching. Every observation Webb makes adds to the catalogue of the cosmos's earliest moments. Every spectrum it measures tells us something about the chemical history of the universe that we could not have known before. And every discrepancy between what it finds and what the models predicted is, in the deepest sense, the most valuable thing it can give us. Not confirmation, but direction. Now, as we approach the end of tonight's journey, let's allow ourselves to sit with everything we've encountered. We started with a telescope, a machine that took 30 years and $10 billion to build, one that was almost cancelled twice by the same Congress that eventually funded it through to completion. One that had to be engineered in 18 foldable mirror segments because no rocket in existence could carry it intact. One that deployed itself alone 1,000,000 miles from Earth through 344 mechanisms, each a single point of failure, none of which could be tested all at once before launch, and none of which could be repaired after. Everything worked. It unfolded in the cold dark between Earth and Sun. It cooled itself to 233 degrees below zero. It aligned its mirrors to within 8 nanometers, and it opened its eyes on the most distant light in the observable universe. What it saw was not what we expected. It saw galaxies where the models predicted only proto-galactic seeds. It saw chemical complexity where there should have been primordial simplicity. It found oxygen, element of life, product of stellar deaths, in a galaxy that formed only 290 million years after the Big Bang. And it confirmed that the universe is expanding faster than the standard model predicts, not by a small residual, by an amount that has grown more significant as the measurements have grown more precise. The universe has been keeping secrets from our models. Roger Penrose is in Oxford with his equations. He proved something in 1965 that the physics community found uncomfortable and eventually accepted. He has spent 20 years developing a framework that proposes our Big Bang was not a beginning, but a transition, a seamless mathematical continuation from a previous cosmic eon, a universe that lived out its entire history before ours and left in the conformal structure of space something that became our birth. He may be right, he may not be. The universe is patient, and it has never demonstrated any particular concern for how quickly human beings arrive at the correct description of it. Newton worked until it didn't. Einstein corrected Newton and extended physics beyond what Newton could reach. Quantum mechanics revealed a layer beneath classical physics that classical physics had no tools to even suspect. Each of these transitions took years or decades or generations from the moment the first anomaly appeared to the moment the larger framework arrived to contain it. The anomalies are here. The framework has not yet arrived. That is where we are. What stays with me tonight is something simpler. Somewhere in the long dark between galaxies, in the silence that separates the stars, in the cold that fills the void, there are photons that have been traveling since 290 million years after the Big Bang. They left a galaxy already showing signs of chemical history. They threaded through 13.5 billion years of expanding, evolving, cooling universe, through the formation of the Milky Way, through the ignition of our Sun, through the emergence of life on one small rocky planet, through all of human history, through 30 years of design and construction for a telescope they would never know was waiting. And then they arrived, and we caught them. We built something capable of catching light that ancient, of spreading it across a detector, of reading in its wavelengths the story of a universe that was doing things we hadn't predicted. We built something that could look at a galaxy 13.5 billion years away and find oxygen in it, and know what that means, and be surprised by it, and go back and check and confirm that yes, this is real, and now we have to think harder about what the universe was doing in its first few 100 million years. That is what science actually looks like. Not a triumphant march from ignorance to certainty. A conversation, slow, painstaking, frequently surprising, with a universe that is under no obligation to be what our models assume. We asked what the first galaxies looked like. The universe said, something you didn't expect. We asked how fast it was expanding. The universe said, faster than your model predicts, and it does not matter how many times you recheck the measurement. We asked whether our model of cosmic history was complete. The universe said, no, keep looking. There is more here than you have found. We are looking. We will keep looking. The telescope, 1 million miles from home, has not finished its work. Every night of observing it completes adds to what we know. Every anomaly it confirms pushes the theoretical community to ask harder questions. Every photon it catches from the dawn of the universe is a message written before the Earth existed, arriving now, here, at an instrument we built because we couldn't stop asking what was out there. We built a machine and we sent it into space because we needed to see further back than any instrument had ever seen. We needed to look at the moment when the universe was first becoming itself, when darkness was giving way to light, when hydrogen was giving way to stars, when emptiness was giving way to structure. We built it because the universe at the beginning was the universe at its most fundamental, before time and chemistry and gravity had layered billions of years of complexity over whatever was essential and original in the cosmos. And the universe, when we finally looked, showed us something that our best understanding of beginnings doesn't fully account for, something too massive, something too complex, something that had done too much, too fast. That is not a failure. That is a door. Every time science has found a door like this, a place where observation exceeds prediction in a way that cannot be explained away, what lay beyond it was something new, not a correction, not a parameter adjustment, something genuinely new about the nature of reality. We don't know what lies beyond this one, but the telescope is still watching. Thank you for spending this night at the edge of what we know. If something in tonight's journey moved you, if the universe feels a little stranger, a little larger, a little more worth wondering about, please take a moment to like this video and subscribe to Slow Orbits. It means more nights like this one. Good night.